Okay, now we derive a equation or formula for electric potential due to a point charge. So in this figure, we consider a point charge Q is situated at point O, and we calculate the electric potential at point P at a distance r from it. So as we know that the potential means work done per unit positive charge. That means first of all we calculate the work done. That's why we considered a point A at infinity, where a test charge Q0 is situated at a distance x from O. Okay. So when a test charge Q0 is situated at point A, the electrostatic force acts between them. So the repulsive force, and because both are the positive charge, so repulsive force between that two charges, we know that from the Coulomb's law, F equals to 1 by 4 pi epsilon naught Q0 by x square. Now we consider the another point B at a small distance dx from A. So the small work done in moving a test charge Q0 from A to B through a small displacement dx against the electrostatic force is dw equals to F dot dx. And because this direction is a force and this direction is a displacement, this is a 180 degree. So F dx 1 cos 180 degree, cos 180 value minus 1. That's why we get minus F dx. So first of all, at point A, the test charge is situated. Electrostatic force between them is this one. So force is exerted this side, but we move this unit positive charge from A to B through a small displacement dx against this repulsive force. So the small work done dw will be right like this way. Okay. Now the total work done, because total work done means A to B, this is dx. So B to C, we consider the small displacement ds. C to D, like this way we get a small amount of work done, and if we add it, that means we integrate. So total work done in moving the unit positive charge Q0 to at point P. So W equals to integration of dw. Dw value is minus F into dx, infinity to R F dx. Now we put the value of our expression of F here, and we solve this integration. We get W equals to 1 by 4 pi epsilon naught Q0 by R. And we know that work done is stored as a potential energy inside the body. So by the definition of electric potential, V equals to W by Q0. So W means this one divided by Q0, Q0 cancel. So we get Q by 4 pi epsilon naught into R. So V equals to Q by 4 pi epsilon naught into R. And in the first chapter, we get the expression for electric field E equals to 1 by 4 pi epsilon naught Q by R square. Okay, you remember these two things. For potential only R and electric field R square. Don't confuse. Now if we draw a graph, potential and electric field versus the displacement, or that R with R, because E proportional to 1 by R square and V proportional to 1 by R. If we plot a variation of potential and electric field E with R for a point charge, we get this type of diagram. Here you see that E proportional to 1 by R square and V proportional to 1 by R. So if the value of R equals to 1, in that time E and the value of V will be equal, because 1 square means 1 and 1 by 1 also 1. So this is a coinciding point at point when the value of R is 1. But after that, if R equals to 2, here 2 square means 4, here only 2, it will be increases. So this line is the potential, because after that it will increases. Okay, and this one is the electric field. After that it will be decreases. This is 1 by 4 and this is 1 by 2. Okay. So this is a variation of potential V and electric field E with R from point charge Q. Now we discuss the electric potential due to a dipole. We also know, you know the concept about the dipole. In first chapter we also derived some formulas And here also at the same point we derive the electric potential at an axial point and at an equatorial point. So first of all, we find out the electric potential at an axial point of a dipole. So here we consider AB is a electric dipole consists with 2 point charges minus q and plus q separated by a distance 2a. We calculate the electric potential at point P at a distance r from its center. So first of all, we calculate the potential due to minus q and potential due to plus q. But here you must remember, you use the sign. In electric field we use only the magnitude, but here when you find out the potential, minus q means here you also write the minus q. So V1 is the potential due to minus q charge, minus q by 4 pi epsilon naught 1 by r plus a, not the square. Okay, potential equals to 1 by r. And the potential due to plus q by 4 pi epsilon naught 1 by r minus a. Now the total potential V1 plus V2, the V1 plus V2, if we put the values, so we get q into 2a by 4 pi epsilon naught r square minus a square, and we know that 2a into q, this is nothing but the electric dipole moment. So V equals to P by 4 pi epsilon naught r square minus a square. P is the electric dipole moment. Now the special case, if a very short dipole, that means if r square is very greater than a square, then we can write V equals to P by 4 pi epsilon naught r square. So P is constant, 4 pi epsilon naught is constant, so we can write V proportional to 1 by r square. Okay. Now the electric potential at an equatorial point means the bisector, perpendicular bisector of the electric dipole. So at point P at a distance r from its center, we calculate the electric potential due to this electric dipole. So first of all, we find out the electric potential due to minus q, that is V1 equals to 1 by 4 pi epsilon naught minus q by r square plus a square to the power half, because this is root over, because this is the triangle, right angle triangle, so this is the hypotenuse. If this is a, this is r, so this will be root over of a square minus a square plus r square from the Pythagoras theorem. Similarly, V2 equals to, we get, because this side also same, r square plus a square. So we get 1 by 4 pi epsilon naught q by r square plus a square to the power half. Now the total potential at point P, V1 plus V2. So this is minus q by this one plus q by this one. So both cancel each other because magnitude is same. So equals to 0. So you remember electric potential at an equatorial point of a dipole must be 0. Clear? Thank you. In next class, we discuss the electric potential at any general point of a dipole. Thank you very much.